And our next speaker is Hanchong Liu from Tsinghua University, Associate Professor at the Center for Statistical Research, board member of Young Statistics Association, and several boards, and highly published as well. So I'm looking much forward to the talk on randomization and covariate adjustment in split plot designs.
Thank you for the nice introduction. And it's my great pleasure to share our work on re-randomization and covariate adjustment in split plot designs. This is joint work with Wenqi Shi and Anqi Zhao. So split plot design arises from agricultural science with experimental units often known as subplots nested within groups often known as whole plots. For example, if we want to study the effect of two irrigation methods, factor A, and two fertilizers, factor B, on crop yield. In this particular example, it is often not possible to apply different irrigation methods to area smaller than one field, but it is possible to apply different fertilizers to smaller areas. So here, each field is a whole plot, and it is divided into smaller areas called subplots. Then we can assign the hard-to-change factor, the irrigation, at the whole plot level by a cluster randomization, and then assign the easy-to-change factor at the subplot level by a stratified randomization. The split plot design provides a convenient way to accommodate hard-to-change factors and can avoid interference within whole plots. If the whole plot sizes and the proportions of treated units for the subplot intervention within each whole plot are constant, then it is called a uniform design. Otherwise, it is a non-uniform design. In the split plot design, we can also observe many baseline covariates. For example, in a split plot design with students as subplots nested in the classes of in the whole plots of classes, then class characteristics such as class size and teacher experience are the whole plot covariates. And the student characteristics like race and gender are the subplot covariates. The randomization can balance those covariates on average. However, for a particular treatment assignment, covariate imbalance often exists. Regression adjustment and the re-randomization are widely used in experimental results to ensure covariate balance and improve efficiency. However, existing literature on the theory of regression adjustment and re-randomization often assumes that the treatment were assigned at the unit level or at the group level, but not both. So leaving it for the theory for split plot design an open problem. So our work is to fill this gap. And our main contribution is as follows. We call a split plot re-randomization as a split plot design combined with re-randomization to balance covariates. In this work, we propose two split plot re-randomization schemes and derived asymptotic distributions of widely used average treatment effect estimators under the proposed split plot re-randomization and demonstrate the efficiency improvement relative to the classic split plot randomization. So consider a split plot design with two factors of interest denoted by A and B, taking values in 0 and 1. This generates four treatment combinations denoted by Z equals AB, where A and B index the level of the factors A and B respectively. Consider a population of N units nested in W groups with possibly different sizes MW. Here, each group is a whole plot and each unit is a subplot. And we will index the S unit in the W group as WS. And let alpha W denote the whole plot size factor with mean 1. And for uniform design, alpha W equals 1. As I introduced earlier, the split plot design assigns the treatment to different combinations in two stages. In the first stage, it assigned the factor A at the whole plot level by a cluster randomization. That is, it randomly assigns WA whole plots to receive level A of factor A, and then assign the factor B at the subplot level by a stratified randomization, that is randomly assign MWB units in the whole plot W to receive level B of factor B. And the final treatment of the subplot WS, denoted by ZWS, is then a combination of the level of factor A received by the whole plot W and the level of factor B received by the unit WS. So in this assignment, we know that the probability of a whole plot assigned to the level A of factor A is WA divided by W, and the probability of a subplot assigned to the level of factor B is the MWB divided by MW. And since the cluster randomization and stratified randomization are independent, then the probability of the subplot assigned to the treatment combination AB is the product of the PA and the QWB. We will use potential outcomes framework to define causal effects, denote by YWXZ as the potential outcome of the subplot WX and the treatment combination G. And we will use Y bar Z to denote the average potential outcomes. The main effects and the interactions in split plot design can be defined as linear contrasts of the average potential outcomes. For example, the main effect of factor A is defined as the mean of the average potential outcome with A equals 1 minus the mean of the average potential outcome with A equals 0. Similarly, we can define the main effect of factor B and also the interaction tau AB. If we let Y bar as the vectorization of the Y bar G, then this three factor effect in a vector form tau equals G times Y bar, where G is the contrast matrix. So we for each subplot, we observe the outcome and denoted by YWS. To estimate the factorial effect tau, we can first estimate the average potential outcomes. Here are two widely used estimators. The first one is the Howitz-Thompson estimator, which is basically an inverse probability weighting estimator. And it is unbiased, but it is not invariant to location shifts. So to solve this problem, another widely used estimator is the Hayek estimator. It is equals to the ratio of the Howitz-Thompson estimator of the average potential outcome and the Howitz-Thompson estimator of a constant 1. Then by plugging in, we can obtain the Howitz-Thompson and Hayek estimator for the factorial effect tau. So under some moment conditions, Zhao and Ding 2022 show that both the Howitz-Thompson and the Hayek estimators are asymptotically normal. And the asymptotic covariance consists of two parts. One is the S star, which is somehow the scaled within whole plot covariance of the potential outcomes. And the psi is the between whole plot covariance. So in the experiment, we also observe many baseline covariance denoted by XWX, and we want to balance those covariance at the design stage. And in the following, we propose two re-randomization schemes based on the Mahalanobis distance. Specifically, let S hat HTZ and S hat HAJZ as the Howitz-Thompson and Hayek estimators for the mean of the covariance under the treatment Z. Then intuitively, a balanced assignment will result in homogeneous S hat Z, such that the linear contrast of S hat J should be close to 0 for a balanced design. Let tau hat star X denote the linear contrast corresponds to the main and interaction effects, then it is intuitively close to 0, if the assignment is balanced. So we can use the Mahalanobis distance between tau hat star x and 0 to measure the covariate imbalance and to perform the re-randomization. For a predetermined threshold D, the re-randomization accepts the treatment assignment if and only if the Mahalanobis distance between tau hat star x and 0 is smaller than or equal to D. Under mild moment conditions, both the Howitz-Thompson and Hayek estimators are jointly asymptotically normal. And this theorem provides the basis for deriving the conditional asymptotic distribution of tau hat star given the re-randomization scheme M star. Here, star can be HT or HAJ for the Howitz-Thompson and the Hayek estimator respectively. And by this theorem, the Mahalanobis distance convergence in distribution to a chi-square distribution with 3L degrees of freedom. It provides a guidance for us to select the threshold D. For example, we can choose D as the alpha quantile of a chi-square 3L to get an asymptotic acceptance rate of alpha. We show that under re-randomization M star, the asymptotic distribution of tau hat star is a convolution of a normal component and a truncated normal component. Moreover, the asymptotic distribution can be conservatively estimated by a plug-in method. We also showed that the asymptotic variance of the tau hat star under re-randomization is smaller than that of the tau hat star under randomization. And this implies that the re-randomization can improve the asymptotic efficiency. Moreover, we can use a worst type confidence region, which has an asymptotic coverage rate greater than or equal to the confidence level under the split plot re-randomization. And the area of the confidence region is smaller than or equal to that under classic split plot randomization. So far, we consider to use re-randomization to balance covariates at the design stage. Alternatively, we can also adjust the covariate imbalance in the analysis stage. We consider two covariate adjusted methods for both the Howitz-Thompson and Hayek estimators. The first strategy uses the regression formula proposed by Zhao and Ding following the idea of Lin. And the second one is a new method, which is obtained from a projection of conditional inference perspective. Here we assume that in the analysis, we have more covariates than in the design stage. So I will use V to denote the covariates used in the analysis stage. Zhao and Ding have already showed that the Howitz-Thompson estimator can be recovered from the following ordinary least squares fit of an aggregated outcome. And the Hayek estimator can be recovered from a weighted least squares regression. So the straightforward way to adjust the covariate imbalance is to add the treatment by covariate interactions in the above two regressions directly. And this method was actually proposed by Lin in 2013. And if we let beta height and weight height denote the point estimator and the associated cluster robust covariance estimator, here the subscript AG denote refers to aggregated regression, and the WLS refers to weighted least squares, and the L refers to this regression is from the Lin's regression. And by plugging in these estimators, we can obtain the regression adjusted Howitz-Thompson and Hayek estimator for the factorial effect tau and the associated covariance estimator. And we show that under re-randomization, both the regression adjusted estimator are asymptotically a convolution of a normal and a truncated normal distribution. Moreover, the covariance estimator is a conservative estimator. Note that different from previous results on re-randomization, the asymptotic distribution of the regression adjusted estimator is not normal, but still a convolution of a normal and a truncated normal. The reason maybe is as follows. Linear regression is somehow equivalent to projecting y hat star z onto v hat star z for different values of z separately. However, this separate projection is different from the joint projection of the vector y hat star onto v hat star due to the dependent structure, such that the covariance term sigma star are not equals to 0 in general. Moreover, the regression adjusted estimator cannot guarantee efficiency improvement over the unadjusted counterparts. In some special case, for example, if only whole plot covariates are used, then the regression adjusted Howitz-Thompson estimator is asymptotically normal, with asymptotic variance smaller than or equal to the unadjusted estimator. However, we cannot guarantee efficiency improvement for the regression adjusted Hayek estimator, even only whole plot covariates are used. To address this problem, we proposed a projection of conditional inference-based estimator. The idea is easy. Since tau hat star v and tau hat star are jointly asymptotically normal, so conditional on tau hat star v, the tau hat star is still asymptotically normal, but with a mean shift and a covariance smaller than or equal to the unadjusted estimator. So if we can plug in the projection coefficient or to remove the bias, then we can obtain a more efficient estimator, and we denote it by tau hat star p. We show that the projection-based estimator under re-randomization is asymptotically normal, and the asymptotic variance is no greater than the unadjusted estimator under re-randomization. Moreover, the asymptotic covariance can be conservatively estimated. This corollary compares the relative efficiency of the Howitz-Thompson estimator and the Hayek estimator. If the average of the covariance and the potential outcomes are 0, or the whole plots are of equal sizes, then the unadjusted and the projection-based Hayek estimator and the Howitz-Thompson estimator are equally efficient. And if the design is uniform, only whole plot level covariates are used, and the variability of the potential outcomes within each whole plot is bounded, then the Linz regression adjusted Howitz-Thompson estimator is also asymptotically equally efficient as the Hayek estimator. Suppose that only whole plot level covariates are used, then the covariate adjusted Hayek estimator is asymptotically more efficient than the Howitz-Thompson estimator if the whole plot has similar average potential outcomes, and vice versa if the whole plot have similar total potential outcomes. In practice, since the whole plot totals are often more heterogeneous than the whole plot average, so we prefer the Hayek estimator in this case. In the special case of only whole plot covariates are used, we can also adjust the whole plot factor in the Linz regression and let tau hat HTL alpha denote the analog of tau hat HTL that further adjust for the whole plot size factor. And we can show that tau hat HTL alpha under the corresponding re-randomization scheme is optimal among all the estimator and the re-randomization methods considered. Here are some simulation results, and we consider two types of covariates. The first one is only whole plot covariates. The second one is that the covariates vary within each whole plot. And in the design stage, we use the first element of the covariate to perform re-randomization, and in the analysis stage, we use all of the covariates. And the potential outcomes are generated by linear models with quadratic terms, and we perform the split plot randomization and the re-randomization for 2,000 times to evaluate the finite sample performance of different estimators. For the re-randomization, we set the threshold D to be the first percentile of a Cassidy square distribution, implying an asymptotic acceptance rate of 1%. This figure shows the results for only whole plot covariates are used, and the method with R&D is the estimator obtained under classic split plot randomization, and all other methods are obtained under re-randomization. The first row shows the bias of the estimators. Although these estimators are asymptotically unbiased, they may have a small finite sample bias. The second row shows the standard deviation, and we can see clearly that both re-randomization and the covariate adjustment can reduce the standard deviation and thus improve the efficiency. Moreover, the Howitz Thompson estimator that adjusts the whole plot size factor performs the best, which is incoherent with our corollaries. The third row shows the empirical positive bias of the standard error estimators, which indicates that the covariance estimators are conservative. And the fourth row shows the coverage probability of 95% confidence intervals. We can see that all these coverage probabilities are above 95%. This is also due to the conservativeness of the covariance estimator. And the last row shows the mean confidence interval length, and which again shows that re-randomization and regression adjustment can improve the inference efficiency. So to conclude, we propose two re-randomization methods to be used under the split plot design, and we study the asymptotic properties of the Hayek and Howitz Thompson estimator under the proposed re-randomization schemes. We make the following recommendations. When only whole plot level covariates are used, we suggest Linz regression adjusted Howitz Thompson estimator that includes the centered whole plot size factor as an additional covariate. And when subplot level covariates are used, we suggest the projection-based estimator because in theory, it can guarantee efficiency gains, but the Linz regression cannot. That's all. Thank you.
Thank you, and just on time. We have time for a single question. Something that I was wondering, because some of the mathematics they look absolutely right, but also a bit cumbersome. Is it implemented in software, the projection methods?
Yes, we use R to code all the methods, but we haven't made a package right now.
Okay, but maybe a code available, or are you
available?
And is the package coming, you think?
I think it will come in soon.
Okay. Wonderful.